Hello, and two. Statistics is the study of how we collect, analyze, and draw conclusions from data sets. So it is a huge and valuable tool that you can use to bring the future into focus and answer some key questions about your data set and definitely about your businesses. So welcome back to the channel and welcome back to Excel Island, where the goal and objective is to learn and master Python over the next 100 days. Today is day 44. We will continue from our course, the current course that we are on, which is Introduction to Statistics. So we've covered chapter 1 of this course on the previous live streams. We started chapter 2 yesterday, which was day 43, where we are looking at random numbers and probability in Python, in statistics in general. So we are looking at how to generate random samples and measure chances using probability. And we're going to work with a real-world sales data set and calculate the probability of a salesperson being successful. This is what we are going to be doing in this second chapter of Introduction to Statistics course, which is part of the 9 course. We are on the 7th course out of the 9 courses in this data analysis with Python or curriculum on DataCamp platform. So yesterday we learned all about what are chances, how to perform chances or probability with or without replacements, and we did some probability calculations also. Let me just show you what that looks like real quick. We did some sampling probability where we calculated the probability of a product being picked in a samples of products. I also look at some probability with replacements, without replacements. We did some simple analysis also. So you can catch all of that on the 43 live stream where we looked at these lessons. So we're just going to continue from where we stopped on day 43. So we are on this course, Introduction to Statistics. So we've covered a couple of lessons here. So we are on the chapter 2, which is random numbers and probability. So we've learned what are chances. We understood what chances are, what probabilities are. We learned how to calculate probabilities. We did some sampling deals. So that was all we did on the 43. So we just continue from here and look at the next lesson, which is discrete distribution. So I want to know what discrete distribution looks like. So if you want to catch up on the previous lesson, just go to the live stream tab on Excel Island YouTube channel so you can pick up from there. So without further ado, let's continue.
In this lesson, we'll take a deeper dive into probability and begin looking at probability distributions. Let's consider rolling a standard 6-sided die. There are 6 numbers, or 6 possible outcomes, and every number has 1/6, or about a 17% chance of being rolled. This is an example of a probability distribution. In this
Hold up a minute. Okay.
lesson, we'll take a deeper dive into probability and begin looking at probability distributions. Let's consider rolling a standard 6-sided die. There are 6 numbers, or 6 possible outcomes, and every number has 1/6, or about a 17% chance of being rolled. This is an example of a probability distribution. This is similar to the scenario from earlier, except we had names instead of numbers. Just like rolling a die, each outcome or name had an equal chance of being chosen. A probability distribution describes the probability of each possible outcome in a scenario. We can also talk about the expected value of a distribution, which is the mean of a distribution. We can calculate this by multiplying each value by its probability, 1/6 in this case, and summing. So the expected value of rolling a fair die is 3.5. We can visualize this using a bar plot, where each bar represents an outcome, and each bar's height represents the probability of that outcome. We can calculate probabilities of different outcomes by taking areas of the probability distribution. For example, what's the probability that our die roll is less than or equal to 2? To figure this out, we'll take the area of each bar representing an outcome of 2 or less. Each bar has a width of 1 and a height of 1/6, so the area of each bar is 1/6. We'll sum the areas for 1 and 2 to get a total probability of 1/3. Now let's say we have a die where the 2 got turned into a 3. This means that we now have a 0% chance of getting a 2 and a 33% chance of getting a 3. To calculate the expected value of this die, we now multiply 2 by 0, since it's impossible to get a 2, and 3 by its new probability, 1/3. This gives us an expected value that's slightly higher than the fair die. When we visualize these new probabilities, the bars are no longer even. With this die, what's the probability of getting something less than or equal to 2? There's a 1/6 probability of getting 1 and 0 probability of getting 2, which sums to 1/6. The probability distributions you've seen so far are both discrete probability distributions, since they represent situations with discrete outcomes. Recall from Chapter 1 that discrete variables can be thought of as counted variables. In the case of a die, we're counting dots, so we can't roll a 1.5 or 4.3. When all outcomes have the same probability, like a fair die, this is a special distribution called a discrete uniform distribution. Just like we sampled names from a box, we can do the same thing with probability distributions like the ones we've seen. Here's a data frame called die that represents a fair die, and its expected value is 3.5. We'll sample from it 10 times to simulate 10 rolls. Notice that we sample with replacement so that we're sampling from the same distribution every time. We can visualize the outcomes of the 10 rolls using a histogram, defining the bins we want using np.linspace. Notice that we have different numbers of 1s, 2s, 3s, and so on, since the sample was random, even though on each roll we had the same probability of rolling each number. The mean of our sample is 3.0, which isn't super close to the 3.5 we were expecting. If we roll the die 100 times, the distributions of the rolls looks a bit more even, and the mean is closer to 3.5. If we roll 1,000 times, it looks even more like the theoretical probability distribution, and the mean closely matches 3.5. This is called the law of large numbers, which is the idea that as the size of your sample increases, the sample mean will approach the theoretical mean. Time to solidify your knowledge of probability distributions.
Okay, interesting. So let's look how we can understand probability distributions. So creating a probability distribution. So a new restaurant opened a few months ago, and the restaurant's management wants to optimize its seating space based on the size of the groups that come most often. On one night, there are 10 groups of people waiting to be seated at the restaurant, but instead of being called in the order they arrived, they will be called randomly. In this exercise, you investigate the probability of groups different. In this exercise, you investigate the probability of groups of different sizes getting picked first. Data on each of the 10 groups is contained in the restaurant groups data frame. Do we have access to this data frame? Let me check. Let me check my data sets. Oh, we don't. Do we? Why don't we have access to it? No. So we are still on chapter 2, definitely. Yeah. So we don't have access to the data sets. So I'm going to practice here alone. Remember, the expected value can be calculated by multiplying each possible outcome with its corresponding probability and taking the sum. So the restaurant groups data is available. Pandas is loaded as PD, or NumPy is loaded as MP, and matplotlib.pyplot is loaded as PLT. So let's see what we need to know about discrete probabilities. So we need to calculate, investigate the probability of groups or different sizes getting picked first. Okay, restaurant groups, group size. So we need to create a histogram of restaurant groups and show plots. Okay, so it says create an histogram, a histogram of the group size column of restaurant groups, setting bins to 2, 3, 4, 5, 6. Remember to show the plots. Restaurant groups dots. So the data frame is restaurant groups, the group size. So it's going to be dot ist, dot histogram. So you want to create an histogram, and we have to set the bin size, create a histogram of restaurant groups, and show the plots. We have to set the bin size. Bins will now be equal to setting the bins to this number here. Let's copy this number and see what we have here. So it's going to be plt.show. We don't need to label them yet. Plt.show. See what we have here. You can see. So the bin size are 2, 3, 4, 5, 6. Just as we have here. So we are getting there. So next is, so where can I get rid of this? Let me make this a little bit bigger. Let's say next is to count the number of each group size in restaurant groups. I want to count the number of each group, the numbers of each group. This is 6, this is 1, this group size is 2, and this is 1. Okay, let's see. So count the number of each group size in restaurant groups data frame. Then divide by the number of rows in restaurant groups. Number of rows is 6 here. To calculate the probability of randomly selecting a group of its size. Save as size distribution. We set the index of size distribution. Rename the columns of size distribution to group size and prob. Okay, let's take a deep breath and solve this. Can I get rid of this? Okay. So it says count number of each group size in restaurant groups. So the number of each group size in restaurant groups. So you can use our count there. So it's going to be restaurant groups. So size is going to be restaurant groups. Nope. Let me just copy this data from here. Restaurant groups dot value counts. Value count is going to count the number of group size in the restaurant group, then divide by the number of rows in the restaurants. Number of rows, that is, you can use len of restaurant groups to get the number of rows. So to calculate the probability of randomly selecting a group of its size. So this is we are calculating the probability of randomly selecting a group of its size. So you save the result as size dist. So next is to reset index and rename columns. So size dist is going to be size distribution. Is going to reset index. Then we're going to rename the column. So we're going to rename the column to group size. Rename the columns to size dist to group size and prob. Okay. So this is going to be group size. So size this dot columns, groups, group size, and finally props. Props. So let's run the code. Oh, what's our error? Length miss my expected axis has 3 elements. Oh, okay. My length, I think the mistake is from my length. Let's get up on the error. So the error is coming from size this. So size this is supposed to be group size. So the error indicates that there is a mismatch in number of elements when you are trying to rename the columns of size this. Specifically, it says that the expected axis has 3 elements, but you have provided only 2 values. Okay, I think there's a mistake somewhere here. Group size, you change it to, I can't see this very well. Okay, let's copy this then. What is my mistake there? But I'm still getting the same error. Length mismatch. Oh, what is the error here? Oh, let me take a deep breath and try to solve this. Size this dot columns. The instruction says save as size, rename the index of size this. Rename the columns of size this to group underscore size. Correct. Then prob. So what's now the error there? Why are you getting this error? Let's get up on the error. Okay, something is missing somewhere. Let's go back to our value counts. So size this restaurant groups. Oh, I made a mistake somewhere here. In my probability distribution, restaurant groups. I didn't mention the group size I'm counting. I'm counting the group size column. I didn't mention that. So I didn't count the number of record in each group size. Now let's run the code again. Oh, group size. It's saying restaurant group is not defined. What do you mean restaurant group is not defined? Restaurant groups. Okay, this is groups, not groups. Oh, come on. We're still getting an error. So this should be our result by now. We nailed it there. But let's see, we are still getting an error somewhere. Oh, correct. So that we solved that. So our mistake was not mentioning the group size when I was doing the value count. I didn't mention the column I wanted to count. Now let's move on to the next challenge. So it now says calculate the expected value of the size this, which represents the expected group size by multiplying the group size by the probability and taking the sum. Ooh. I wish I could do this in my Jupyter notebook. Oh, come on. Why did I have access to these restaurant groups or data frame? Oh, come on. This is not fair. Let me do something. These restaurant groups. I just want to see how many record we have there. Look at the restaurant group data set we have here. Just group ID and group size. So group ID of A, the group size is 2. Okay, it's just a simple data frame that we are playing with. Nothing that much or big. Group ID of B, they have 4 people in the group. Group C, 6 people. Okay. So let's just practice what we need to practice there. So it now says calculate the expected value of the size this, which represents the expected group size by multiplying the group size by the probability and taking the sum. Okay, let's see how to do that. So we've done create probability distribution, we've done this. We set the index, we resetted the index here. We renamed the size group column. So we need to calculate the expected value. The expected value. So expected value is going to be NP sum. So we're going to be summing the size this column. You sum the size this data frame that we did here. Sum size this by multiplying the expected group size by multiplying the group size by the props. Sum size this column, then multiply by group size. Coding is so size this the group size column. They want to multiply it by the prop. Multiply by size this prop. I'll just copy this. But I want to multiply by the props. The prop here, the probability of that. So let's run the code. So the expected value is 2.9. Interesting. So now calculate probability of randomly picking a group of 4 or more people by subsetting for group of size 4 or more and summing the probabilities of selecting those groups. Okay, let's see how to do that. So subset groups of size 4 or more. Let's sum the probabilities of group 4 or more. Interesting. So we want to subset for groups. So we are going to select the size this data frame. Size this data frame. Open square brackets. Size this data frame. I'm going to select group size, the group size column. That is subsets. Group size. column. Oh, where is this? Did I go back there? It's supposed to be here. So let's do that again. I'm trying to select the group size column here. So let's be size this. So I'm selecting the group size column, the group size, the group size column for where the group size is greater than or equal to 4. So then we sum the probabilities of group size 4 or more. So to sum that, so that's going to be group size 4 or more, which is this data frame. Then the probability column, top column dot sum. So let's run the code and see. Voila. So the probabilities of randomly picking a group of 4 or more people by subsetting for the group size is 0.3%. Interesting. So there's stereo distribution utilization. So you continue to build upon these skills since many statistical tests and methods use probability distribution as their foundation. Probability distribution is kind of technical a little bit. You have to understand probability or terminologies. Interesting. So let's move ahead. Oof, that was quite a lot. So let's look at identifying distribution, expected value versus sample mean. Let's see what we can do here. So identifying distribution, which sample is most likely to have been taken from a uniform distribution? From a uniform distribution, wh- which sample is most likely to have been taken from a uniform distribution? Definitely is B. So impressive identification. Since the histogram depicts a sample and not the actual probability distribution, so each outcome won't happen the exact same number of times due to randomness, but they are similar in number. Okay, okay. So expected value versus sample mean. So the app to the right will take a sample from a discrete uniform distribution. So which includes number 1 to 9 and calculate the sample's mean. You can adjust the size of the sample using the slider. Note that the expected value of this distribution is 5. A sample win $20 if the sample's mean is less than 4. There's a catch. You get to pick the sample size, which simply is which sample size is most likely to win you the $20. Okay, I think the higher the distribution. Okay, let me read that again. Expected value. What is called expected value versus sample mean. So the app to the right will take a sample from a discrete uniform distribution. So which includes the number 1 to 9, okay, and calculate the sample's mean. You can adjust the size of the sample using the slider. Note that the expected value of this distribution is 5. So a sample is taken and you win $20 if the sample's mean is less than 4. There's a catch. You get to pick the sample size. So which sample size is most likely to win you the $20? But the sample mean is what? The sample mean is the expected value is 5. Okay. The sample mean is 6. Take another sample. Let me see. The expected value is 5. So this is 5. So we say which sample mean is 4. The sample mean is 4.5, but I need it to be 4. I need it to be 4, not 4.5. Okay, let's do it again. Oh, 100. You know, let's do 1,000. 4.89. Ah, God, that's so much. 5.0. It is moving forward. I need to move back. This is 5.2. Oh, can you see that? 4.8. 5. Expected value is 5, but the sample mean, which sample size most likely to win the $20? The sample mean is less than 4. A sample is taken, you will win $20 if the sample mean is less than 4. What about the sample mean? I'm not even seeing the sample mean here. The sample mean is 5. It has to be less than 4. Hmm. This is 5. This is 5.1. No way. Uh-oh. That's too much. Hmm. Hmm. This is getting higher. One last try. But this is giving me the sample mean of 5. But I need the sample mean that is less than 4. Okay, now let's stick to that. Let's say multiple samples there. So I'm still falling within the range of 5, 4.9, 5.02. Oh, so okay. If you do 100 is, so you can see, try again. Larger values will likely be closer to the expected value of 5. So it's going to be lesser value. Is that 10 or 100? It's definitely 10. It's definitely 10 because 10 will be less than the expected value, 4 or less. So nice work. Since the sample means will likely be closer to 5, the expected value with larger sample size, you have a better chance of getting a sample mean further away from 5 with a smaller sample. Exactly. So let's see continuous distribution. Should we do that today? Or we come back and do this tomorrow? So we need to, number one is continuous distribution, or the binomial distribution, and stuff like that. All right, so let's stop here for today. I think we've covered quite a lot today because these are highly technical terms. All right, so that'll be the end of the live stream for today. So if you enjoyed this learning journey with me, I'll do well to support the channel by giving the video a thumbs up, this live stream is a thumbs up, and get access to the data set so you can practice your probability skills also over there as I do that over here too. So do have a wonderful rest of the day, and I'll see you on the next video on the channel and on the next live stream day 45 as we continue our knowledge and solidify our knowledge on statistics. Bye for now.